Yeah, thanks, Lars. So it's a great honor to present my recent work here at UChat. And I would also like to thank Andy, who supervised the whole project. So, okay. All right, so in first part of this talk, I will introduce the conventional electron hydrodynamics and together with its application to some recent experiments. And in second part, I'm gonna focus on the hydrodynamics of an electron-phonon system. And I will show you that the transport coefficient in that system is quite different from the conventional electron hydrodynamics. I will also at last compare to a recent experiments in PTSM4, where people find strong electron-phonon interaction dominant flows. Okay. Well, to begin with, for like a generic many-body quantum system, the dimension of Hilbert space is always proportional to the d to the nth power, where d is the number of degrees of freedom for each particle, and n is the number of particles. Well, for a classical computer, we may find exact solutions for like 20 or 30 numbers of particles, but in reality, the real materials can contain numbers like 10 to the 23. So, well, for like if you are interested in only ground state energy, the finite size scaling results might be okay for you to do the exact solutions to attack the physics in that material. But however, if you focus on the whole dynamics of the system, which inevitably involve all the excited eigenstates, it might not be good enough. So, well, even though you cannot get the full knowledge of the full dynamics, one may ask what else? I mean, what the universal feature that we can get from out of this quantum system. So the lesson from statistical mechanics tells us that generic quantum system will thermalize on large time scales. And after thermalization, many modes would decay rapidly, while only those that has conserved quantities are long-lived. So if people are interested only in the long-lived mode, the conserved quantity could be a good starting point. And yeah, or equivalently speaking, this is saying that you just effectively integrate out the decaying modes and focus on the long-lived modes. And this might serve as the spirit of hydrodynamics. So we say that we believe many-body quantum system would behave as a classical fluid on long time and length scale. And if we incorporate the conservation law, we get the hydrodynamic equation. As a warm-up, I would like to introduce the charge conservation as an example. So the charge conservation locally can be written as the continuity equation for the charge density. And people do the derivative expansion of the current operator in that continuity equation in terms of the charge density. Well, since the derivatives is kind of 1 over L or say 1 over T, it's a good small parameter in this expansion. To the leading order and plugging back to the continuity equation, we get famous fixed law, or the, if you like, it's called diffusion equation, and D is the diffusion constant. So this equation describes the late time dissipation dynamics of the charge density, since the D coefficient here is Brooks time reversal symmetry. Okay, so that's for charge conservation. If we want to generalize above results to the conserved charge energy and momentum, we'll get a continuity equation on the left-hand side. And on the right-hand side, that's the first order derivative expansion of the current operator. Well, apart from the incoherent conducting matrix term, the rest piece of this equation is really the textbook Navier-Stokes equation. like the eta here is a shear viscosity describe the transverse momentum dissipation, and the delta is the bulk viscosity that is the viscosity that apart from the shear viscosity one. Well, those terms that I'm not named here is are all the thermodynamic quantities. Okay, so here I introduced the incoherent conductive matrix as an extra part. This term really describes the current that is not carried by the momentum, but carried by the fluctuation of chemical potential or the fluctuation of temperature. So for example, if you are considering the relativistic fluid, like the charge neutrality point of graphene, we have the electrons and holes. And in that case, the electrons and holes would flow in opposite direction, which means that the momentum is zero. Well, but the holes will have this opposite sign of the charge with the electron. So in that case, there's still some current. And that's the that current is not caused by the momentum transfer, but caused by the strong particle-hole interaction. And under other limit, like the Galilean-invariant fluid, it's not the incoherent electric conductivity that is non-zero, but the incoherent thermal conductivity is non-zero. That's basically due to the non-linear dispersion relation. Okay, so from this hydrodynamic equation, routinely we can linearize these equations away, about the diffusion away from the equilibrium and get the diffusion mode and sound mode. So here I show you the two diffusion modes. The first one is from the transverse channel, and as expected, it's from the shear viscosity. And the second one is from the longitudinal channel, and it's caused by the incoherent conductive matrix. Apart from this diffusion modes, we have the sound mode, and also from the longitudinal channel. At the leading order, it has a linear dispersion with the coefficient V as the sound velocity. And if we include the second order correction to the dispersion relation, we have the dissipation term, the gamma S here, which is also called attenuation constant. And this attenuation constant, this kind of dissipation will include both the energy, charge, and momentum. Okay, so that's for hydrodynamic theory. So how can we really see this hydrodynamics in real material? So let's first consider ordinary metal. In ordinary metal, we have only few electrons, but many impurities. And in that case, electrons would scatter off the impurities very strongly, which means that impurity scattering length is much smaller than the electron-electron scattering length. And so we say that the macroscopic, the physics underlying this region is basically the electron impurity scattering length, which relax the momentum very strongly. So in order to get a hydrodynamic equation, to get a conserved quantity, we need to make the metal clean enough such that the impurity scattering length is much larger than the electron scattering length. Well, there are, so in the right-hand side, we show you the rough picture about that. Like we decrease the impurity density in that material in experiment such that the electron-electron scattering is dominant. Well, that is not enough because we also have Unkelab effect for the electron-electron interaction. So in order to have totally momentum conserving electron-electron interaction, we need to lower our temperature scale and also make the Fermi surface small enough. And that's basically the region we are interested in. Okay, so to see exactly the hydrodynamics in experiment, I would like to highlight a recent experiment by imaging the current distribution through constrictions in graphene. So the basic experiment setup for this for it is considering a current flow across a constriction with finite width and thickness, and they use the cutting edge image technique the NV center to detect the current distribution across constriction. And their result is very nice. And for example, at the room temperature, for both hole doped or electron doped case, they found a 2-peak profile here. And by comparing to the theory, they find that the mean field path in this temperature scale is dominated by the momentum relaxation. Here, momentum relaxation really includes all the scattering event that relax the momentum. And we call it ohmic regime because the momentum is rapidly relaxed macroscopically. Well, once we decrease the temperature, the current profile starts to concentrate near the center, mimicking the classical viscous flow. And this viscous region is really dominated by the hydrodynamics because further evidence is that when we compare to the theory, we find that now mean field path is given by the electron scattering length. So speaking of this experiment, I would also advertise our recent work about spatial imaging of quantum criticality. So as you can see here at charge neutrality point of graphene, it's not captured by the kinetic theory since there's no well-defined Fermi surface. So I and Andy now have some results that, have a draft like talking about the spatial imaging problem of a quantum criticality, just like the charge neutrality point of graphene. And we are using the holographic model to tackle this problem. Okay, let's move on. Another experiment that is very interesting to us is the signature or breakdown of Wiedemann-Franz law. So Wiedemann-Franz law really say that in a normal metal, like the normal metal that is dominated by the momentum relaxation scattering, the thermal conductivity over temperature times electric conductivity is given by a number, a constant, which is called Lorentz number. Well, that's not true. That's not hold for the hydrodynamics as shown in both theory and experiment. The Lorentz number now will attain a prefactor, a ratio which is smaller than 1 and which depends also on the scattering rate. So on the right-hand side, people find the clear signature of this variation of Lorentz number in some materials, some electronic materials. Okay, so in previous discussion, we really treat the electron interaction as the dominant one and treat all other events, scattering events as some kind of momentum relaxation. Recent experiments on PTSM4 show using the thermal power to show that at a temperature around 10 to 20 Kelvin, there is a strong phonon drag peak. And this strong phonon drag peak really means that at that region, the electron-phonon interaction cannot be neglected. So a natural question to ask if we treat the electron-phonon interaction as the dominant one, and also we assume that it's momentum conserving and neglect the Wolfram effect, how do the hydrodynamic coefficient change? So before answering this question, I would give you a big picture of the physics in that region. So since the momentum of the electron and the phonons, as a whole party cannot be relaxed, but the momentum can be exchanged between electrons and phonons. So we expect that the electron and phonon would flow as a single unified fluid. Okay, so our model is like this. I would like to state again that we consider acoustic phonon that interact with electrons with momentum conserving interaction, and the electrons would live on an isotropic Fermi surface. So Yeah, and again, we treat the electron-phonon interaction to be momentum conserving, and then neglect the Wood-Clark effect in that region. So the excitation window for the electrons is proportional to the temperature, while for the phonons is proportional to a t to the d square, this power, where d is the dimension of the space. We expect that the low temperature is still like a very like electron dominated fluid, while at high temperature is probably a phonon dominated fluid. So a natural question to ask is what happens in between this temperature in the intermediate temperature region.
Can I ask the question?
Okay, sure. Yeah.
So if you consider the electrons and phonons as a single fluid, right? Then what exactly is flowing?
So well, it's just a combination of these two. I mean, like
well, see, if we talk about regular hydrodynamics, then we know it's a flow of mass, right? Then if we talk about electronic transport, we usually talk about the flow of charge, right?
Okay.
So in graphene, there is a slightly different situation than the hydrodynamics in graphene corresponds to the flow of energy, right? Now here, right? And there in graphene, you can say, okay, there are two sort of constituents of this fluid, electrons and holes, right? And then the spectrum is such that in the end you get the flow of energy. But these two constituents, electrons and holes, they're very similar, right? They're both charge carrying, they have similar spectrum and so on and so forth.
Yeah.
Now here you have electrons and phonons, and even though the electron-phonon interaction, you could say that for the combined system, it does conserve momentum. But it does transfer momentum from electrons to phonons. In these two things are typically very different, right? So that's why if you want to consider this combined system as a sort of one single fluid, then in this hydrodynamic description, this typical velocity, right, this flow velocity, you have to be able to say what exactly is it carrying, what quantity.
Yeah, I mean, I will show you the transport coefficient, which makes this description more clear. And the quick answer to your question is like, for example, the momentum susceptibility is in the intermediate temperature region is dominated by the phonons, while some other quantity is still dominated by electrons. So it seems that, I mean, part of the quantity is given by the phonon, while part of the quantity is given by electron. And I think that's kind of like rough picture about this flow. Yeah, I will tell you more about this hybrid fluid in the following discussion about transport coefficient. And
say related, it's basically the same thing, right? Conventionally in the textbooks you learn that phonons transport heat, electrons can transport heat, and phonons not transport charge. Right? So I guess your answer will basically be related to the heat transport. That you may contemplate that you have a sort of a single fluid, correct?
Yeah, definitely. So we here assume that only electron can transport the charge, and both can transport heat, and there's some interplay between these two guys. So
maybe if I can jump in also. Hi. One way we can think about this is that, I think in the old language, one thing you might have done is say, okay, let me write down some hydrodynamic equations for the phonons, and then some hydrodynamic equations for the electrons. And then you would just add some kind of artificial timescale that into your system that basically allows you to dump electron momentum and phonon momentum, so to combine or to conserve, the sum, but to exchange momentum between the two parts and energy between the two parts. And so what we're doing is basically just sort of skipping that intermediate step and going directly from kinetic theory to sort of the actual unified hydrodynamic description. And indeed, it's not like there's a single particle that's flowing in the fluid. As he'll show, you really have these kind of exotic hybrid electron-phonon sound modes, for example, that that genuinely have characteristics of both. You can't say it's electrons moving or phonons moving individually.
Yeah. Yeah. Thanks, Andy. Yeah, I think I can move on.
I have a question, probably just to add on this discussion a little bit. I just want to relate with what we know from usual plasma physics. In typical plasmas where ions are, let's say, free to move, these acoustic modes are actually due to the fact that ions are shielded by the electrons, and then you have this shielded motion that makes interactions between ions short-ranged, and then they support some sort of acoustic mode. Here, I suspect that is slightly different, right? Because the phonon mode already, there's a bare phonon mode that doesn't really rely on electrons. So in that aspect, well, of course, probably I will wait until I see the final form of the equations, and most likely we're going to talk about this. But I just wanted to understand whether or not you treat your phonons as, let's say, a wave equation, and then you sort of consider field for this deformation, and then you get some sort of adiabatic elimination of the phonon degrees of freedom, and you get effective equation for electrons, or you treat, let's say, two equations separately, and then you couple these two equations. Thank you.
Well, so yeah, we couple equations by the electron-phonon interaction. Yeah, as you just said, we treat like phonons as itself and the electrons itself, but couple the Boltzmann equation with the electron-phonon interaction together.
Okay, thank you so much.
Okay. Yeah, as I just said, to tackle this question, we use the kinetic theory, which is also known as the Boltzmann equation. And since hydrodynamics can tell us what is the dispersion, we really need to do the macroscopic calculation of the scattering rate. So in order to solve this equation, we linearize and get the deviation from the equilibrium. So to further facilitate our formalism, we introduce the Dirac notation here, and the phi can be think about as the deviation from the equilibrium for the distribution function. And in the product is defined here. And from this notation, we can really get the linearized collision integral as the matrix. So since we are assuming as the tropic Fermi surface, we have a good rotational symmetry. So we can decompose each mode in terms of the rotational invariant basis. As an example, I show here the momentum, the current, and the heat current can be written in this basis. And all the thermodynamic quantities by doing the right inner product can be written out. And I will relegate these details into the paper. So let's focus on the macroscopic scattering rate. As I just said, it can be written as a matrix, and the phi is chosen by our settings. So it's actually a very well-known result, which is the Brauch-Grönius temperature that separates two different scalings for the scattering rate. So at very low temperature, the phonon momentum is approximately given by the temperature over phonon velocity. And if you integrate this momentum over all the phase space of the phonon, you will get famous T to the D+2 scaling. And if you consider like n equals to 1 mode, since it itself gets a temperature suppression, so the scattering rate for this mode after normalization is T to the this power. Well, so the temperature, the critical temperature that makes this picture very different is the Brauch-Grönius temperature, which makes the phonon momentum at the same order of the Fermi surface momentum. So above this temperature, the electrons can scatter off each other on the Fermi surface very randomly. And the scattering rate in that region, I mean, high temperature region, is really the linearity resistivity. Okay, so equipped with this knowledge, let's look at the transport coefficient for the hydrodynamic equation. So first, let's see the sound velocity in the sound mode. The sound velocity is given by the thermodynamic quantities, and we see that in the intermediate temperature region, it has a job with respect to the temperature. This is because at a very low temperature, the momentum susceptibility is still given by the mass of the electrons. While once we increase the temperature above into some very high temperature, you can expect that the flow now is really the energy flow, which means that the velocity is really determined by the phonon velocity, because the phonon has, as I just said, much more excitation and excitation window when temperature is very high. Well, some weird thing happens in not weird. I mean, so to interpret these two velocity, we need to get some temperature dependence of the sound velocity, and that is basically the job here, the job in here. This is because the momentum susceptibility in this intermediate temperature region has a temperature scaling dependence, while in the denominator, the charge and energy density is still given by the electron, and that makes the sound velocity to job. Okay, so apart from the sound velocity, the linear dispersion, we have a attenuation constant correction to the sound mode. As plotted in the first figure is the ratio between the bulk viscosity and shear viscosity. We see that this scaling is no longer the Fermi liquid-like scaling. This is actually expected since we have different macroscopic scattering events compared to the electron-electron scattering. What more interestingly is that when we increase the temperature above the T4, remember the T4 is the temperature that sound velocity starts to drop, we get the incoherent fluid, which really means that the incoherent conductivity now is larger than the shear viscosity and dominate the dissipation of the sound mode. The reason why we think that it is really a hybrid fluid because first it's incoherent, because the coherent fluid can only be like the Galilean-invariant electronic fluid. So if we went into a region where incoherent conductivity is stronger than shear viscosity, it's kind of like the phonon effect is not negligible, and we may have the so-called hybrid fluid there. So to sketch out the phase diagram of the temperature dependence, we see that at low temperature is the Galilean-invariant fluid, while above T4, we call it hybrid fluid, but it's anyway. So at very high temperature is governed by the relativistic phonon modes. Okay, apart from the sound mode, we can also have a plasma dispersion relation correction to a sound mode. This is really induced by the long-range Coulomb interaction. So, yeah, for the temperature below T6, we find the conventional plasma dispersion relation, but with the coefficient have the same temperature dependence as the sound velocity. While above T6 temperature, the dispersion relation becomes more interesting and depends on the scale that you are interested in. When you are at very long distance, is plasma-like, but if you decrease the distance into some intermediate scale, it has like a sound dispersion, but with the dissipation momentum independent. And if you decrease the distance into very short region, it recovers the sound like dispersion relation. The last thing that I want to mention about hydrodynamics is the magnetic field effect. So the magnetic field is introduced by incorporating the Lorentz force acting only on the electrons into the Boltzmann equation. And I just want to emphasize that in our setting, we only find that the phonon effect will be there in the shear viscosity, but it's absent in the Hall viscosity. So if we define the ratio like this, we see that without phonons, the ratio won't depend on the magnetic field, but with phonons, this ratio is a decreasing function of momentum. And this phenomenon can serve as some, protocols for experiments to see the electron-phonon hydrodynamics. Okay. Last, I want to talk about the application in real materials for this electron-phonon hydrodynamics. And so recall that the Wiedemann-Franz law tells us that the thermal conductivity over temperature times electric conductivity is a constant. But here, as you can see, in the intermediate temperature region, we see a very strong variation of the Wiedemann-Franz law. This is basically because at that region, the conductivity here and the thermal conductivity here is no longer obeys the Wiedemann-Franz law. So to see it more clearly, I want to compare it with the recent experiment on BTSM4. From this experiment, we can extract the Brough-Grunitz's temperature to be around 25 Kelvin. And the change of the scaling of the thermal conductivity, which is 8 Kelvin, can give us the relative impurities, relative electrons impurity scattering strength, which is around 0.04 for this system. And these two information together will give you the minimum of the Lorentz number based on our theory, which is 12.7 Kelvin. And this really is very close to the experimental result, which is around 14 Kelvin. Okay, so another check on this experiment is by considering the T4 temperature. I want to mention again that T4 temperature is not from the impurity scattering, but purely from the hydrodynamic equation. And from this experiment, we can estimate the T4 to be 5 to 6 Kelvin, and we find a strong variation of Wiedemann-Franz law is indeed locates between this T4 to Brough-Grunitz's temperature region. And as I said before, this region is really the emergence of the hybrid fluid. So, well, it's not a rigorous proof, but we can state, we claim that this kind of hybrid fluid is associated with the strong variation of Wiedemann-Franz law. Yeah, okay, so yeah, there are many outlooks that I want to state here. So first one is that we expect more experimental evidence for this prediction of a hybrid fluid in between T4 and Brough-Grunitz's temperature region. Second part is that since we are only considering it as a tropic Fermi surface, well, for the real material experiment, Fermi surface cannot be purely isotropic. There are some anisotropic thing happening there. So it might be interesting to incorporate our theory to an anisotropic Fermi surface. Well, the last thing I want to mention is that there are some evidence about giant thermal Hall conductivity in insulators. Although we are focusing on the metals, but it's still interesting if we can incorporate the multi-band phonon modes together, say with the Berry curvature structure of the phonon modes into this formalism to see what else can be happen in our electron-phonon hydrodynamics. All right, so I would like to conclude this talk with a table of several different temperature regions. And yeah, thanks for your attention and happy to answer your question.
Thank you, Xiaoyang. I mean, we've already had discussions, of course, but I'm guessing there are more questions. So if you have questions, please speak up.
Maybe I can ask another question. We know from the usual theory that if electron-phonon interaction is strong, then they can form sort of bound states or sort of combined objects, which are called polarons, right? Now, sometimes people even, or some time ago, people even made a theory when these polarons could form something like Cooper pairs and create superconductivity out of this, right? So you, when you are making this hydrodynamic theory of combined electron-phonon system, then probably you assume that the electron-phonon interaction is strong enough to thermalize everything. So can you compare the strengths of electron-phonon interaction that's required for your thermalization to the strengths that's required to form polarons? Because I'm assuming that you don't want polarons in your description.
Yeah, I didn't do that comparison, but yeah, I mean, if you are looking at late dynamics, I don't think we have polarons in this. But yeah, I think, yeah, I don't know, but yeah, we just did do that comparison.
So further questions?
Yeah, but I have something. In a way, yeah, there's several issues, right? So one issue is that it's also textbook material that usually at somewhat higher temperatures, the thermal conductivity is anyhow dominated by phonons, right? So how do you distinguish that you have your coupled phonon electron system from having them just in essence independent, right? And so I don't know better than the textbooks cry out, you know, normally electrons go their way, phonons go their way. They may, you know, scatter each other a bit, but thermal conductivity is a phonon thermal conductivity at higher temperatures. Don't worry about electrons, blah, blah. So where's the difference?
Oh, so what's the question again?
The question is elementary. Read Ashcroft and Mermin, right? People have been measuring thermal conductivities, electroconductivities, blah, blah, since the beginning of times. And Ashcroft and Mermin will tell you that normally people have analyzed this in terms of A, you have your phonons that are moving, B, you have your electrons that are moving, right? And thermal conductivity at higher temperatures is completely dominated by phonons. It's you know, complete textbook. So the question arises, where do I see the difference between the textbook discussion and this claim that you can have, you know, basically one hydrodynamical liquid? What is the signature in experiment?
Well, yeah, I guess the textbook really tells us the two extreme limit of this phase.
No, it's the other way around, gentlemen. We're still waiting for definitive evidence that actually the kind of, you know, merged hydrodynamics exists. Right? There's a history of about 100 years or 200 years of measurements saying no, they just go their own way.
Well, I mean, one thing I would.
So you have to demonstrate where the difference is. Come up with a smoking gun experiment, demonstrating the difference, right? Where is it? That's my question.
Well, if you go back to this, the like thermal conductivity, et cetera, slide with some of those plots, it's towards the end. Yeah, here. So the 14. Yeah, like actually, if you look at these plots, they aren't that different from what textbooks say you should expect. And I think part of the issue here is that like just looking at these global transport coefficients, like global bulk thermal conductivity or bulk electrical conductivity, this is kind of not the best experiment to look for evidence of hydrodynamics because it's very sensitive to impurities. I mean, I think what we would advocate for, what I would advocate for at the least, is looking at more kinds of local type probes, whether that be imaging or even just the kind of non-local resistance type setups that GAIM did, back in 2015. I think the best way of detecting this would be to see evidence for all of the sort of exotic temperature dependence in hydrodynamic coefficients that we've predicted, not all of which has been presented, but you can read this long paper that we wrote if you're interested.
So Andy, the strongest claim I have encountered in the last many years for this kind of combined hydro is basically that cobaltate material, right? Basically coming out of Andy Mackenzie's industry in Dresden, right? And they were basically argued we see an extremely low resistivity over an extended temperature range, right? And usually you would say that the electrons dump the momentum in the phonon system, but when they move together, right, there's no momentum dissipation, and therefore the resistivity is so low. Does it fit in your expectations for this kind of hydro?
Well, okay, so I think palladium cobaltate is maybe sort of a subtle thing. My personal view is that the most recent experiments suggest that this is basically a ballistic system at temperatures maybe below 50 Kelvin, and there's experiments that justify this, and I think that's a separate story. But like I said, I think that.
But Eddie, you expect at 50 Kelvin that the electron-phonon coupling, the normal GaAs, right, will basically limit the mean-free path of the electrons, and
yes,
how explain then that very low resistivity, right? That's sort of smoke in there's extreme anomalous. That's not happening. Right? That's exactly the point. Where are the phonons out there?
Yeah, I mean, okay, look, I agree that there are a lot of sort of numerical details that are surprising in that material.
It's really, Andy, I'm really not aware of any other system, especially not made out of things containing oxygen, right, where you find such a low, as how you call it, rather temperature independent resistivity up to relatively high temperatures. Right, normally phonons racket, right? They kick in at low temperatures and start to drag away the momentum. Also, when you're in a ballistic regime, this matter just mean field, mean free path of the inlet mean free path of electrons that get limited.
So, I mean, if you wanted to look for evidence of the electron-phonon fluid in that system, as I mentioned before, I think you could naturally try to do either maybe local imaging probes or non-local resistance, constriction, conductance, etc. Lots of experiments to try to locally get at the viscosity directly, and then looking at the temperature dependence of that viscosity. We predict it, it will look, quite different if you have electron-phonon scattering versus electron-electron scattering, as one example. As was mentioned, studying Hall viscosity may also be valuable, to help distinguish between electron-electron versus electron-phonon dominated regimes. So
final question is, it's also again textbook. So we measure the thermal conductivity. You are in this phonon-dominated regime. Usually there's a nice big peak occurring at a rather low temperature for the reason that only when the phonons are strictly linear, they don't see the umklapp, but at the moment that you start to pick up the curvature of the phonon dispersion, you start to pick up the umklapp scattering associated with the phonons, right? And that basically produces a peak where at low temperature you're basically kind of a momentum conserving like transport by the phonons, and then they start to umklapp, and the thermal conductivity decreases rapidly. Now, graphene is very special, right? Because they're extremely stiff phonons, but they are something like a platinum tin 4. I bet that this phonon peak would be expected at a rather low temperature. Usually it's like 50 Kelvin or something. Don't ask me precisely. It's again ask of the Mermin material. So isn't that something to worry about big time when you go away from graphene?
Well, personally,
It's not about opinions. This is about textbooks. This is about 200 years of experience with doing measurements in the lab, you know, and getting completely credible explanations as well. I mean, these phonon peaks are very, very well understood. And you just assume that you have perfectly linear phonons, but the question is whether that assumption is satisfied, you know, in the material you're looking at. And graphene is okay, I believe it, but the platinum tin 4, I don't believe anything of it.
Well, okay, I think we certainly will admit that, as mentioned, studying anisotropic effects is sort of an important future direction, because surely that will only add.
And we know the answers. It's all an ask of the Mermin. Don't reinvent wheels, you know. Phonons don't necessarily conserve momentum, unfortunately.
Well, I mean, if you have a regime where phonon Umklapp is strong, then you're not going to expect electron-phonon hydrodynamics. So I guess if that's...
Yeah, but the bottom line is the only material that you perhaps could expect that, you know, reasonably speaking, knowing all these things in ask of the Mermin is perhaps graphene, you know. And nearly everything else, we just know that phonon transport gets extremely incoherent at temperatures above sort of 50 Kelvin or something, right? It's kicking at low temperatures for Umklapp.
Yeah, are there further questions? I mean, I would have a rather technical one. Like I think I just missed that one, but how exactly do you like include the disorder in your analysis now? Is it like only in the electron sector? Is it in the phonon sector? Is it in both, or?
In both.
It's in both. Okay. And how sensitive?
Yes. Yeah. We call it differently. Like we use the subgrid E for representing electron impurity scattering, etc. Well, for phonons, we use the subgrid phonons for that.
Okay. Okay. And is it very sensitive? Like, are these results very sensitive to how you do that in practice, or?
Well, yeah. I mean, yeah, it is indeed sensitive. Like here, like in the last plot, if you change the electron, the impurity strength, the variation will vary a lot. But the point is that, yeah, basically in between the T4 and T Brownian temperature, there is still a strong variation of the Lorentz law. But you are right, it highly depends on the impurity strength. If you want to, if that is a question.
Okay, thank you. Are there any further questions?
Oh yeah, by the way, I want to add more comment here. So if we equate the impurity strength for the electrons to be equal to the phonon, and as I plot in the in this insight, it is indeed that a strong variation of the Lorentz law will approach the T4 temperature region. And this is given, I mean, the details is given in the paper, but we can show that it is indeed approaching the T4 temperature. So in that sense, like, again, the impurity is equivalent for the electrons and phonons. I mean, the strength is equivalent, and we may expect a strong variation without too much sensitivity on the impurity strength.
Yeah, thanks. Are there further questions?
Maybe I'll just have a comment,
Sure.
which is specifically on this slide that we're seeing now. There are these plots for Lorentz number, right? And it just so happened that I recently I had to do something, and I looked up how this Lorentz number looks in regular normal materials, right? So, for example, in regular bulk copper, right, the Lorentz number looks very similar to what you show here, right? At low temperature, it starts off at L0 more or less, and then at very high temperature, it's back at L0, and then at some intermediate temperatures, which is something between 10 or 50 Kelvin, that sort of range, there is a broad minimum such that this Lorentz number drops down in value, perhaps a factor of 2, right? And then it goes back at high temperatures, and so that's how it looks, right? Depending on the purity of copper, these curves, they change a little bit, but the main overall shape is the same, right? So yeah. Therefore, the one that this plot for this PTSN4 that you show now, it actually doesn't look surprising at all. It looks very, very standard, right? If you compare this with the violation of the Wiedemann-Franz law in graphene, there the situation is different because first of all, it's violated on a much higher scale. The Lorentz number reaches 20 or something times this L0, and the Lorentz number is large, right? So the violation occurs towards the Lorentz number being larger than L0. Whereas in standard materials, it seems to go below more or less like it's drawn here, right? So therefore, it's just a bit of a comment that this sort of plot does not always mean something unusual, right? Of course, there could be something unusual there as well, but since we don't expect anything unusual in bulk copper, then you know, it doesn't mean necessarily that once you see a plot like this with the change by a factor of 2 or something towards the decrease of the Lorentz number, that there is something necessarily unusual there.
Yeah, I agree. I mean, yeah, so the violation of Wiedemann-Franz law is not so mysterious. And it's I believe that for any like metals that away from the normal metal limit could have this kind of features.
Okay, are there any further questions or comments? Well, if not, I would first like to thank Xiaoyang again for the nice presentation. And I would also like to say that we have a talk next week already by Inia Mauri from Utrecht University. He will talk about work he does in collaboration with Henk Stove. And then 2 weeks later, basically in 3 weeks from now, we will have Andy Mackenzie talk about the latest experiments, and Andy Lucas already hinted at it, like he will talk about actually ballistic signatures in some of these systems that were discussed here. And yeah, so I hope to see many of you next week and also in 3 weeks. And yeah, have a good evening, have a good night, morning, whatever. See you.